as soon as this is fixed, this whole work situation, hopefully we can invite you in person at some point again.
Okay, I'm live now, so if you want to start.
Okay. Yeah. So for everybody, welcome to the seminar for today, and just be aware that we are already recording the session. So please, for the attendance, keep your camera and mic shut down for the talk, and then later for the final discussion, if you want to do face-to-face, we'll be happy for you to put the cameras and so we can see who's talking. But for the presentation, let's keep it off so we avoid problems with the connection. And Florian, well, first let me introduce our speaker for today. We are really lucky to have Florian accepting to give us a little bit of his time to give us a talk today about one of the latest developments he's been working with his team at DeepMind, Bootstrap Your Own Latent. That, well, it's not just this approach, but also some follow-ups and following works on self-supervised learning techniques. As most of you know, this work is having a impact in the community, so we are really happy and lucky to have one of the main authors explain it in first person to us. So thanks a lot, Florian, for accepting this invitation. And well, I think the biography details, we have it on the website. It's not really worth it to spend too much time. But well, Florian did the PhD in France, and he was also collaborating with the Mila lab in Canada during his PhD. And after that, he went to work at DeepMind, where he is now, doing really interesting and impressive work. So Florian, I don't want to take more of the time, so the floor is yours. Thanks again, and whenever you want.
I think also forgot to mention that we've been working together on a European project for 3 or 4 years.
Yeah. It's thanks for the note. Yeah, actually, Florian is not any colleague; is a very close colleague. We've been working together in a European project for a lot of time during the PhD. So yeah, we are also very happy in that respect, to see you here. We've been following your career, we can say, since the beginning of the PhD. So it's really nice to see where you're getting. So again, thanks, and the floor is yours.
So thank you very much. Thanks a lot. So I'm going to do a presentation about the work I did in collaboration with many people. So feel free to interrupt me at any times. Very roughly, this talk is going to be divided into 4 parts. At the beginning, I'm going to give a kind of a small introduction about what we call self-supervised learning. And I'm going to just be assuming that you have basics in deep learning, nothing more. Then I'll speak about this method, Bootstrap Your Own Latent. And something that I was missing when I was attending presentation is how an idea came from, what make it happen. So there's going to be the third part of my talk on what was the initial intuition when we started the project, not at the end of the project, which is quite different. And finally, we'll do some extension about how this approach has been applied to other domains, such as reinforcement learning, robotics, and video. Okay, so let's start. And again, do not hesitate to interrupt me. So again, the thing that is very important is we should not forget that the work I'm going to present is really the result of a collaboration of many people there. Some people coded, some people put their expertise, and people provide us research advice. But it's really teamwork. On DeepMind, when you see a paper with so many authors, it's because a lot of people are involved. I really want to emphasize it. It's a teamwork. So first, self-supervised learning. So what is the goal of computer vision? In computer vision, you have an image, and you're going to feed it into a model in order to solve some kind of different task at hand. You can do classification, segmentation, object detection, depth estimation, plenty of things like that. But how does it work in practice? At the beginning, you're going to take your image and you're going to feed it into an encoder, a neural network. And then you're going to have another network that is going to be specialized on your what we call downstream task or downstream network. So this model is going to be decomposed into a head, the downstream network, and into a torso, an encoder or a pre-trained network. But the question is, how are we going to train this encoder? So most of the time in deep learning, what you're going to have is a kind of a pre-training stage where you take your image, you're going to train this encoder by having some very predefined task. In the case of vision, is going to be classification. Why? It's because in classification, just for historical reasons, we have this very large image data set called ImageNet. So you have a lot of labels and a lot of images. And because it's a very rich signal, you can use this classification task in order to pre-train an encoder. When you're over with this classification, what you can do is you can remove this encoder, and then you can put another head that is going to be specialized on the downstream network. And now, because you already pre-trained this big network, you only need a few labels to train on very complex vision tasks, for instance, object detection on smaller size dataset. So this is more or less the key intuition on everything works this way in deep learning and vision, and is also starting this way in language now. And of course, you can have many downstream network as you have tasks, but always the same encoder. So if you think about it, the key bottleneck here is not the downstream network or exactly the difficult task that you have at hand. One of the key bottleneck, it is the encoder. So if you improve the pre-training of the encoder, then you improve actually the full pipeline. So improving this encoder improve object detection. And this is exactly what we're going to check about. And how can you improve this encoder? One idea is, okay, just put more data into your encoder. And the other idea is to put better network. And this is more or less the full literature. So for instance, better network, it can be efficient network, it can be transformer, visual transformer, on more data, you collect more data. Here, we're going to focus on this point, which is having more data. The problem is the following, is for now we've been using classifications. So for every image, you have a dog, you have a label. And the problem with that is it's quite costly to collect this kind of data. If you collect a data set, it can cost you millions of euros. And you need to multiply by 10 if you want to have a better data set. So it's not sustainable. So the idea is just, okay, can we use unlabeled data? Because you have plenty of them on the web. And this is what we're going to try to leverage. Can we use this unlabeled data to actually pre-train our encoder? So if I go back to your encoder, what you're going to do is you're going to have what we call a self-supervised or unsupervised learning with a lot of free unlabeled data. And then you're going to have some few labeled data, and you're going to have your downstream network that is trained in a supervised fashion. And what I'm going to focus here is presenting the methods, self-supervised learning methods, to train this encoder with free unlabeled data. So this is the motivation that I'm going to explore here. So what are the classic way to do classic self-supervised learning methods? So if you go back to the early days of unsupervised learning, what you're going to do is image reconstruction. You take your image here, a dog. You're going to put your favorite neural network, for instance, a ResNet, and you're going to extract your image embedding. But here you still need to train your ResNet. So what you're going to do is you're going to have a deconvolution network in order to try to reconstruct your image. But you don't, because you don't want to learn the identity here, because it's useless. What you're going to do is you're going to correct your image by putting some transformation here. So if the network is able to reconstruct the image, then it should be able to learn a good representation of this image. The problem with that is actually reconstructing the full image is very expensive. And even from a higher level perspective, is okay, if I ask you what is a dog, do you need to be able to paint a dog, to draw a dog, to understand what is a dog? Maybe not. Maybe you're going to put too much knowledge into just the fact of being able to pet a dog than actually understanding a dog. And doing this image reconstruction is missing maybe what you want to care about, is learning good image representation that you can use later on. So people move to another paradigm, and this paradigm was called Pretext Tasks. What it is you're going to take an image and you're going to do something like a simple rotation, a transformation that is super easy. A posteriori, what you're going to do is you're going to train your network to be able to actually kind of decode this transformation. So here, you take your image, you rotate it, you apply your ResNet, you extract your image embedding, and you have a classifier which say, okay, it has been turned by 90 degrees. What is nice, it's somehow you're generating new label for free because it's super easy. So you can use unlabeled data. So people have been trying rotation, and exactly what I was saying. Or some people have been trying other things, such as, for instance, you take a crop of this image and you try to locate it into this image. So here, this case, here. People also try colorizations and plenty of other pretext tasks. However, we may have some problem. What's more important if you want to learn a good image representation? Is it a localization more important? Is it being able to rotate the image? Is it better to be able to colorize an image? It's hard. And besides, you're kind of missing what is very important in deep learning. You want to remove what we call human knowledge, human expertise. And here, because you are defining tasks by hand, somehow you're putting back your human expertise. If I ask you, okay, what is a good self-supervised task for I don't know, sound, you have to come up with your own pretext task. So you're missing the full point of deep learning here. So it then comes up with a new generation of algorithm, which is close to what we are interested in machine learning. And those algorithms comes with the following intuition. A view of a dog is still a dog. What I mean by that, if I take an image of a dog, and if I rotate it, if I put some noise, if I resize it, if I change the colors, whatever happens is still a dog. So the key information into an image is invariant to any kind of transformation I'm going to apply on top of it. And this is really crucial to understand. A view of a dog, a transformation of a dog, is still a dog. So one of the first algorithms that worked based on this idea was called CPC, and later simplified and improved with something called SimClear. So what is the idea here is the following. You take an image, you're going to transform it, and this transformation, I'm going to call it a view. And you're going to compare it with another view. So if the two views are the same, it means that it does contain the same semantic information. So it should be the same. But if I take another image, it is not the same, so it does not contain the same informatic information. And if I take another picture of a dog, it's still not the same image. So somehow it does not have the same semantic information. So with this intuition, this is how it was turned into, turned into an algorithm. So you take your image, you take two views. Then each of these views is going to be processed, and it's going to be extracted as image representation. What you're going to put on top of it is you're going to put an MLP to have a projections. There is not a good understanding of what we have this intermediate MLP, but one way to see it is you're bringing a bottleneck, representation bottleneck, which is going to compress the information. And if you compress the information, then you have better representation. So just see it as a compression mechanism. And then what you're going to do is you're going to share the two networks. So the same network is going to process all the views. Finally, you're going to have two representations, Zi on Zi plus whatever index is, and you're going to compute the cosine similarity between the two representations. If it's the same image, good, it should be 1. If it's not the same image, it should be 0. And then you have your training loss. It's possible actually to kind of scale up this idea by just having a lot of image. And instead of saying, is it the same or is it not the same? The loss is becoming the following: is in the list of images here, one of them is the correct one. Find it. You turn your cosine similarity with a kind of a logic with the softmax. So don't be scared with the maths if you don't like maths. It's just a cosine with multiple images. Okay, and if you do that, actually it works quite well. For up to 1 or 2 years ago, it was definitely the state of the art. And what I want to emphasize in this evolution is this idea of human prior in the evolution of self-supervised learning. At the beginning, you have an input, you have your model, and you have a task. Every kind of machine learning algorithm can be defined this way, where you have then an error in order to update your model. And what was important with deep learning is, for the first time in the machine learning community, you remove the expertise while designing the model. And when we think about the evolution of self-supervised learning, it is also this idea of removing this expertise. When you have a reconstruction, you don't have that expertise, but you do put some expertise because you have to define a transformation. And the best drawback that you have to take is being able to have a correct balance between how much human knowledge you're going to put into your training and into your model, and how much efficiency is going to be. If some of you are aware of what is called of Richard Sutton, which is a very famous researcher in reinforcement learning, he has a very small blog post about half a page about the bitter lesson of machine learning. Every time you want to put some human expertise, is always going to pay off, but on the long run, it's always going to be lower. So my goal here is going to remove as much human expertise to have good performance on the long run. So it's nice. I'm giving you a lot of algorithms, but actually how I'm going to test it. So we have this linear evaluation protocol that is kind of a gold standard in self-supervised learning. It has its weaknesses, a lot of them, but it's still quite a very interesting one. So how do you do? As a first step, you're going to train your ResNet with the algorithm we just show you. And then you're going to frozen it, and you're just going to train a linear classifier on top of it. And this linear classifier is going to be trained on ImageNet to adjust the classification. So because it's a linear classifier, if your representation is good quality, it's going to be able to do a linear discrimination of your features. Let's imagine you have plenty of points into a table. If your points are not sorted, you're not going to be able to draw a line to discriminate them. If your points are correctly sorted, you can just separate with a line. It is what we are checking here. If our ResNet is learning good features, then we should be able to easily separate them with a line, a linear classifier. So just also, there is an issue in the animation, sorry for that. Just to give you an idea of the evolution of performance with this self-supervised learning. So if you train with all the labels, all the human information, you have a performance on ImageNet that is between 70 to 80%. If you try to do image reconstruction, then your linear evaluation is going to be between 40 to 60%. So as I told you, trying to draw a dog is not the best idea to understand what's a dog. It is shown here with this linear evaluation. If you try to define pretext task, you improve your score by quite a bit. But because your pretext tasks are highly specialized, then you cannot really reach good performance. And then you have those contrastive methods, CPC, that start reaching full supervised learning because you remove this kind of knowledge. And for the fun history, this improvement from 40% to close to 80% has been done in something like 18 months. Nobody in the community would have expected such a fast pass for such a hard topic. And what I'm going to present here is a new class of methods that is called bootstrapping methods. And they improve on top of contrastive methods and are becoming slowly one of the most interesting ones. Any questions so far? So, BYOL. Again, remember this key intuition. A view of a dog is still a dog. Semantic information is invariant to transformation. So, if you're very naive, what is the best way to say it is the same thing? Well, it's super easy. I take two views and I say, okay, it's the same thing. This view should be exactly the same, whatever the transformation. No need of negative example. Let's go straight to the point. And surprisingly, it's not that easy. But let's see a way how we can do it. So in BYOL, what you're going to do is you're going to take your view here, and you're going again to process it with the encoder. And we're going to have a small layer that is called a predictor. And it's going to output what we call prediction logics. Then, on the other side, we're going to have another network, a different one, that is going to output target logics. Those are the same dimension, but we don't have a predictor here. And what we're going to try here, and something that is very important is these target logics are not trained. And what we're going to, I apologize, I'm a bit mixed up in my own animation. So at the beginning, as you may imagine, all the networks are randomly initialized. And what you're going to try to do is to regress them. Sorry if I lose you. So you have at the beginning random initialized network, and you're going to regress your prediction logics to your target logics. And the idea is what is going to happen if you do that. So the big surprise is if you just do this training loop, even if it's completely random at the beginning, what is going to happen is the following. Your encoder here is going to be slightly better than it used to be before random initialization. So if you just try to regress a random projection, it's completely random at the beginning, but if you just learn this random projection, your encoder, if you evaluate with a linear evaluation, is becoming better. Why? It's because when you do random initialization, actually you're keeping some properties. And if you try to store and learn those properties that are extracted from random initialization, then you're going to improve from the previous step. So a natural next step is the following. It's because this encoder is better, what we want to do is improve those targets. So let's copy my encoder here, and let's try to have new targets that are better quality. And let's try to do it again. And if you do it again, this one's going to be becoming better. So let's do it again. Let's copy it. So this one is becoming a lot stronger, and so on and so forth. This is the intuition that we are using in BYOL, and turns out to be effective in practice. So how do you do it if you want to dig into the details? Again, you take your image, you split it into two views. Like before, you have two ResNet, and you're going to have your bottleneck information. Then what you're going to do, and we start changing from simply, is you're going to have this extra MLP that is called a prediction. And as we're going to see later, this MLP is everything that is important here. Then what you're going to do is you're going to extract your logics from your what I'm going to call the target network. And as I told you, I'm going to compute to the cosine similarity between both of them to regress one to another. Finally, remember, I had this copy aspect. Because we don't want to have one step learning, one step copying, what we did is we applied the exponential moving average to have a slow update of my target network. And if you do that, on BYOL, it works. Nothing else. No trick, no optimization, no cheating, just that. Yes? Juan?
No, go ahead and ask if you want, Juan.
Why in particular this exponential moving average?
So at the beginning, what we had was, we had two networks actually. And from time to time we were training this one, from time to time we were training this one. So we were inverted the stop gradient, if you prefer. It turns out that sometimes it was a bit unstable. Because it was a bit unstable, we thought, okay, it's because your distribution is shifting too quickly. And one way to fix it in reinforcement learning, oh, I forgot to mention, I come from reinforcement learning. So a lot of my intuition comes from reinforcement learning, is to use a target network. Because if you use a target network, what you're going to predict here is going to be slowed down. If it's slowed down, then it's easier to learn. This is the intuition. And then we're going to observe that even if this intuition was valid, it was not what was the most important. But at the beginning, it was just to ease the training. It was a kind of optimization trick.
Thanks.
So BYOLS. What are the key ingredients of BYOL? First, image transformation. BYOL does not work if you don't have image transformations. Then these target networks. These target networks, as we're going to see, it's just an optimization trick. In the end, it's not very important. What is important is the predictor and the stop gradient here. Then the next key ingredient is exactly this additional predictor on top of the online network. And why this method is quite interesting, it's really a simple training procedure. If you look at the machine learning literature, people like doing things that are complex. This one is really not complex. The second point is you don't have to have negative examples. Because as soon as you want to have negative examples, you start thinking, okay, what is a good negative example? How can I define them? Should I try to put a curriculum? Plenty of questions that here becomes irrelevant. Something also, if you're familiar with self-supervised learning literature, people are from time to time using pseudo-labels, a form of clustering. And here, because we're working with embedding on logits, we don't have any more clustering. Yes, what?
So I have another question with this part. But I think it's quite interesting that you don't use the negative examples. But how it works? Like how is possible that it works without the negative examples?
It works because there is this predictor. So for now, I'm not going to dig into why it works, because I want to be sure that you understand the method. Because it's because it seems so simple that you want to ask how it works, but it's because you just understood the method. Well, or if you're familiar, you already know it. I'm sorry for repeating myself. But I'm going to come to this point already.
Okay, thanks.
So performance, I'm going to go very quickly over it because for me, it's not an interesting one. It's what is shining, but not the interesting one. Besides, it's a bit obsolete now. So when we started this paper a year ago, remember it goes very fast. The gold standard was we want to try to beat some supervised learning method with this linear evaluation. So when we started, the landscape was more or less that. And then when we implemented a BYOL, we managed to reach and match supervised baseline in some cases. So we were very happy because we never worked on vision before. So we started on the topic and you reach state of the art. It's quite unusual. But so it was pretty impressive and we're super happy about that. Now, if we want to be super fair, you have people from Facebook, especially Mathilde Caron, that has done extraordinary work. I highly recommend that are more better than BYOL. But I think they still complement. And what is nice is that she also is using bootstrapping. So no bootstrapping method is starting slowly outperforming CPC methods. So this was the gold standard, but nobody cares about linear evaluation in practice. What you care, for instance, is being able to use few labels. So now imagine that you have ImageNet with only 1% of your labels. It turns out that if you train a network from scratch with 1% of the labels, you only have a success ratio of 25%. But if you do your pre-training with BYOLS or some other things, you manage to double its performance. So in other words, because you pre-train your network with unlabeled data, you need fewer data. And this is one of the interests of semi-supervised learning. Now again, you have something that is called Sinclair V2 that perform what we call a distillation procedure and manage to have with 1% of the label the equivalent of what we used to have with 100%. But it's another story, and I highly recommend you reading this paper if you want to dig into few labels learning. It's surprising results that come up with self-supervised learning is when you have few labels, you would expect that the smaller is the network, the better is the performance. If you remember your old lectures on machine learning, is you have a balance to find between number of data versus the capacity of your model. So if you have few capacity, you need fewer more parameters if you don't want to overfit. It turns out that if you have a good initialization, actually it's exact opposite that it's happening. Is the bigger is your data, the better is your performance, even when you have a small amount of data. And this is really one of the big surprises of self-supervised learning. Is over-parameterization is efficient if you have a good initialization point. Well, actually, maybe some people in deep learning literature may have known before it, but for us, at least, it was a big surprise. Yeah, this one not interesting. And then what we care is, okay, fine-tuning classification is nice, but in the end, what is really interesting is to go to very hard tasks, such as what we call semantic information, depth estimation. And what was nice is, thanks to this unsupervised method, you can have better pre-trained models that improve your model, which was our initial goal at the beginning. So again, don't care about the numbers are going to be defeated. They're already defeated. What is important is self-supervised learning. Know it's working. A few observations that are worth of interest is if we compare BYOL to CPC or Sinclair, both are using what we call transformations. In practice, it turns out that BYOL is less sensitive to transformations. Why? So here, for instance, is every time we remove a transformation, we have a drop of performance. So why do we have a bigger drop with contrastive methods? When we try to find which method, which image is a good or the bad one, it's actually super easy, for instance, to find a pixel. You always look, I don't know, to the histogram of colors of your image. And it turns out that if you only look at the histogram of color to your image, it's super easy to discriminate your image to the all other one. And if you want to avoid this kind of collapse or trivial representation where you just discriminate the image by your color, you need to put color distortion or grayscale distortion. And actually, if you don't have this color distortion, CPC methods completely collapse. In BYOL, because we're not trying to find the good one into a list, but just think it's the same, we are by construction less sensitive to this differentiation. In other words, we say it's the same, you choose, and that's all. Sensitivity to batch size very quickly because it's not really interesting anymore. is with CPC, what you care is the more negative example you have, the better it is. So a way to do it is to have large batch size. And unsurprisingly, when you have small negative sample, so smaller batch size, then the performance starts dropping. In BYOL, because we don't have negative samples, we don't have these issues. Here it's more about unsupervised and variance issues. Okay, so now let's answer your question, Juan, because I think it's maybe the most interesting part of the presentation. Here, really don't hesitate to interrupt me. Don't hesitate to ask extra questions. So just a quick reminder, you have your two images, you process them, you do your percent similarity, you have your update, and let's move to the next part. The first thing that you may say is why BYOL does not collapse. If you look at this loss, you will say the best way to minimize this loss is to put 0 all the time. So if you always output 0, or if you always output any kind of constant, your loss is minimal. What is important? So yeah, everyone is the first friction. There is a trivial global minima in this loss. It's a collapse constant. But be aware of something very important here. This is not a loss. Why? It's because we have what we call this EMA target. We are training two networks in parallel. One is your ResNet network with your projection. The other one is your target. So every time you output a gradient, you're only going to change the direction here. But this gradient is not going to update this one. So because of that, when you change that, when you update these elements, your target is also moving. But your target does not move in the direction of your loss, of your gradient, to be precise. Another way to see it is think about GAN. In GAN, you have a discriminator and you have a generator. And it's normal for everyone that when the discriminator is evolving, the generator is evolving. But we're not speaking about GAN loss, we're speaking about dynamic system. And it's exactly what's happening here. It turns out that BYOL, because of this target network, is a dynamic system. It's not a minimization process of loss. So you do have equilibrium that are trivial, but in practice, it turns out that those equilibrium are unstable. Like in GAN, you may have you are looking for saddle point, and you have optimum or equilibria that are unstable, and those trivial ones are unstable. This is very important. It turns out that in practice, what we observe is the equilibria that are stable are the ones that have a good representation. The equilibria that are unstable or not attractive are the ones that actually is a collapse constant. And what?
Is that a question, Íñigo? Do you want to read it? Íñigo, do you have a mic? Do you want us to read it?
Okay. So the question is, what the presentation are from different views? I'm sorry.
I think he was following up in your conclusion. I think he's saying that another it's not a question. Okay.
No,
okay, now
I was trying to add in that, I don't know if it's true, but also as you have two different networks at first, two different initializations, the output is not the same because also there are two different views and only one is optimized. So
But imagine now that all your weights go to a 0, for instance. Imagine, it's not going to happen, but it's a good way to represent it. Then your output become independent of your input. So in that case, if your output become independent of your input, then you minimize your loss. Right? But because it's not a loss, it's dynamic training, then it's not true anymore. If you imagine you have a landscape of optimization, it's like you can imagine your equilibrium to moving, your gradient is moving around and it's never reaching your bad points because it's unstable. It's really, really important to think about dynamic problem. And for the small story, most of the authors of the papers are from mathematical background, and they are expert in optimization, some of them. However, because dynamic problem, they spend like 2 or 3 months trying to look for a proof, but it's so hard because it's a dynamic problem. We look at game theory, we look at fictitious play, all these kind of things, and we could not come up with something. But if I want to explain the intuition with a hand, is you have 2 networks that you're optimizing, but only one is updated with your gradient, and this is why it's dynamic. So here we're just explaining why we are not collapsing. It's not exactly explaining its intuition, but let's move to what are important. Yep. Sorry?
No. I was not saying anything, sorry.
Okay. So now let's move on. What is important components? So let's do some ablation here. So you have your basic BYOL here. And what you can try is, you can try to remove your predictor. And actually, if you do that, you go back to something that is called mean teacher. Mean teacher, that was developed in the semi-supervised setting. But if you remove this predictor, nothing works. In mean teachers, they make it work because they have an extra classification loss that comes with learning. But if you're in self-supervised learning, it does not work. So something else you can do is you put your predictor and you don't use this copy, you should share your weight. What is going to happen is going to be extremely unstable and it's going to barely learn. And later on, we managed to actually remove this EMA, but even if it works, it was not as good as EMA. Another idea is, okay, BYOL is not CPC. So what happens if you also put negative examples in additions? You just put an extra loss with its CPC. After heavy tuning, but really heavy tuning, we managed to increase by 0.2 points, which means that actually negative example does not help in the current BYOL formula. So again, this barely learns. I'm going to come back a bit later on. So the question here is, it turns out that the predictor is really the key. So first question, let's start with the target network. And it turns out that we managed to find a condition to make BYOL work. BYOL does not collapse if, I'm not going to say if and only if because it's too strong from a mathematical perspective, but if and only if your predictor here is optimal. What I mean by optimal is if you just do the regression from your prediction to your projection, and you froze everything else, you have a very small error. So in order to test this idea about, okay, it is very important to have something that is optimal, instead of trying to do some LGD, we turn this MLP into a linear network, and we do Newton optimizations. So we know that at every time step, we are optimal. We have an optimal predictor. And if we do that, we manage to have a good top one accuracy with the linear case, something linear. If we don't do this optimal predictor in a perfect way, it does not work. So if we go back to MLP, then one idea is, okay, if what we care is that our predictor has to be optimal, one idea is that this predictor should be learned faster than the rest of the representation. So it's always trying, if it's always trying to catch up with a moving distribution here of your projection, it's never going to be optimal because the distribution keeps changing. So the idea is, how can we be sure that this predictor is always close to optimal? And there is two ways to do it. Either with the EMA, as you asked for, or for instance, by speeding up the training of this MLP. And one easy way to do it is just to increase your learning rate. And as soon as you increase your learning rate here, and you have a double scale optimization, then it starts working again. Again, not as good as EMA, but still, it's a proof that what is important is to be near optimal. This also intuition, not intuition. Here is this empirical demonstration was also shown by the SimSiam network, if you're familiar with it. And what they did, they just changed this different learning rate by having a loop with multiple gradient steps. So instead of a ratio, you do multiple gradient steps. It's more efficient from an optimization perspective, so they had slightly better results by removing this target network. So what is trying to do? Why this optimal predictor is so important? Without it, there is a strong collapse. So if we look at what this predictor it is trying to compute the expectation. Let's go back to my note because I really want to be precise with this one. So I'll be back in a few seconds. So here, if we look at what exactly this optimal predictor is doing, is computing the expectation of the target projection here. This is this Z epsilon prime. The condition on the online projection. So then, if we inject this expectation into the not exactly loss direction of the gradient condition by this with this pseudo loss, what we're trying to do in the end is trying to be able to minimize the variance of our conditional variance of the target projection here, condition on the online projection here. So now, how can we reduce such a variance? The first idea is actually to remove a variance with that is to have, as we said, a collapse representation. If it is always the same thing here, then we have no variance. But as we saw, this does not happen because it seems to be unstable. So the only way to actually reduce this variance is, which is not intuitive, to increase the variance of Z theta. So the more information you have in Z theta, the more noisy maybe Z theta, the lower is this variance. Then what's happening? You have two ways to increase this variance of Z theta. The first way is by having a lot of noise that is completely random. The second way is actually by structuring your information, because if you correctly capture the semantic information, then you're going to have a good variance because you're going from time to time to change this Z theta regarding your input. And it turns out that it is the second aspect that comes. So your loss is minimizing this variance. Well, the direction of your gradient, sorry, is minimizing this variance. But to minimize this variance, you have to increase this one. And to increase this one, you need to have meaningful features in your representation. Okay, so some people, if you look at what may be other reason why BYOL may work or not work. And some people assume that BYOL works not because of this online prediction, but by other phenomena, that BYOL was doing what we call implicit contrastive learning by using batch normalizations. It's very important for me to emphasize that it is not the case. As a very simple example, this hypothesis relies on the idea that you have batch normalizations. It turns out that you can completely remove batch normalization from BYOL, and you still have state-of-the-art results. So some people think it is because you have implicit contrastive learning. BYOL does not have this kind of contrastive learning in an explicit or implicit way, at least by using batch statistics. We have some elements that tends to show that the predictor somehow is learning kind of implicit negative examples and is doing some CPC in the representation, like if it was memorizing on learning good negative example by itself. But it's really preliminary and we don't have concrete proof of it. So if you're interested in BYOL in general, there is at least 3 papers I will recommend that were doing by other people. The first one is what we Cynthia. So they reproduce most of the BYOL experiments. And in addition, they put a lot of other experiments to give you more additional experimental insight. We did some of those experiments, and it was very interesting to see that some people managed to reproduce it in a completely independent way. If you want to have a better understanding of the dynamic of the training, I would recommend this paper made by Facebook. There are different versions of the paper, and the last one is pretty good. And finally, from Mathilde Caron did a kind of upgrade of BYOL by mixing both bootstrapping and clustering. And it seems to have very promising results. The paper is still a bit early to be sure that it's really the next thing to do. Having said that, the paper is really well written, with plenty of good experiments, and I highly recommend reading it. Okay, so how much time do I have left? Because we may have to make a choice.
Well, it depends on you mostly. The seminar is around 1 hour, the slot, but I think there is no class afterwards. So it depends on you. But let's say until 2, maybe, to leave a little bit of time for questions, maybe, or how much time? I guess you could be explaining us things for as long as we would keep you here. But maybe we can do.
On my side,
what are the alternatives? What are the alternatives that you are thinking?
On my side, I love speaking about the work we did together, so I can speak for hours about it, and I don't have any meeting. On the other side, you may not enjoy hearing me speaking for 2 hours. So here I have more or less two small directions. Each of them may take 10 minutes, 10-15 minutes. One is about trying to what were the first intuitions that we come up with BYOL. So it's more about the history, about when you start a research project. And the other one is what has been done after BYOL, how it has been extended to new modalities. Okay, so if anybody is fast selecting one of these 2 extensions that we can listen for the next 10 minutes or so. If not, I can pick. So if nobody says anything, maybe I would love to hear about the extensions to other type of tasks. Okay. Well, actually, I would love to hear both, but let's keep it just with one of them, and then we can go back to the next one.
Yeah, yeah, exactly. Thank you.
Okay, so it's nice to try a new idea on image, computer visions, But again, what we care in machine learning is that the training protocol becomes independent of the modalities at hand. So what would be nice is, can we extend BYOL to, I don't know, sound, video, graph, or anything? So we have two follow-up work on that at DeepMind that I'm going to quickly introduce. So the first one is after vision, after image, static image comes video. And video are hard for two reasons. Because you have a temporal aspect, because you have sound aspects, so you have multimodal and your temporal. So the work I'm going to present here was mostly realized by those four people, Adria, Pauline, Jean-Baptiste, you. And they collaborate with us because we didn't have the knowledge for video. So I thank them a lot for all the effort they put, and I'm going to present some of their work. So here, the key ideas is to bootstrap one modality into another. So far, we take an image and we say this image is the same as this image. Remember, a view of a dog is still a dog. Now let's imagine that you say, okay, my semantic information are me, you can see me, and my voice. So what I'm going to try is I'm going to bootstrap the picture of me with my voice and vice versa. And if you do that, maybe what you're going to extract is the key information that represents me. And because you're using multiple modality, you may be even filtering what is not important. Maybe you're going to see at some point that what is important is because I'm moving, it's not my background, and it's highly correlated with my voice. So even if I'm moving in another piece, you may be also be correlated to this voice with the fact that I'm moving. So this bootstrapping one modality into another is also a powerful filtering trick to highlight what is important or not. And then something that we completely forget when we're dealing with static information is how can you handle the temporal aspect. And in this paper, this bootstrap one modality into another is going to be quite straightforward. And what they observe and what was one of the key insights is when you bootstrap, it's important to bootstrap a small time to a big image. So you're going to crop on the temporal dimension, and you're going to predict the big picture. Okay. No animation. Okay. So if you do it in practice, at the beginning, you're going to take a small clip of image, just a sequence of image. You're going to have your big network here, FM. You're going to have your projector and your predictor. And for each modality, you're going to have a projector and a predictor. Then you have the exact same thing on the other side, but as I told you, you don't have the same modality. So you may have different kind of networks. You can have, I don't know, here, in this case, it's all convolution network, but you can really change everything here. Maybe you can even put some language and put a transformer here. And actually, you can remove the maybe, you can do it. And you're going to learn representations by doing this bootstrapping. And that's all. It's a direct extension of BYOL. You keep having a small transformation here with basic bit of random Gaussian noise. You have your temporal transformation, which is short clip versus long clip. But the key transformation here is not anymore what is your human expertise, but the different modalities. And what is going to happen is because now you have these different modalities, you actually don't even need strong transformation that you have in images. It's helpful, sure, but it's a bit less helpful. But again, that's all. So by moving to different modalities, we're also removing a bit of human expertise into it. And if you look at the results, no, because it's recent, I can make them shine a bit. So it outperforms the previous methods, including so those are some previous methods that has been done. Some are based on regression, some are based on CPC, some are based on the combination of plenty of loss. But it turns out that just simple bootstrapping on L2 regularization with multimodality outperform all the other approaches. Just to give you an example, this XDC was trained, if I remember well, was trained to have 10 different losses with genetic algorithms in order to correctly balance the loss between all the modalities in order to learn the vision. It's nice, but nobody can do it. It's Google Brain paper. Here, you can implement it even as a student, and it works all the time. And something that is nice is, again, you're reaching and sometimes outperforming supervised baseline. And while in vision, it was we didn't care about the linear evaluation. In video, it's actually quite important because it's really nice if you can pre-process everything beforehand. But well, if you have something to remember, BYOL works on video. If you have more questions about it, feel free to ask about it. And it works with video with few transformations. Then something else that also has been tried. So this time I was not author of this paper, so I really thank my collaborators to share me the slides. It's graph. Graphs are very important if you want to design it. And it turns out that it's super hard to defeat a random projection of graph. It's one of the best representations so far. And you have a lot of different graphs in the wild with different kind of semantic information. And the idea is, no, we're not dealing with image anymore. Can we have different kind of transformation and adapt it to other modalities? And this is what they try. And it's even very important because if you think about graph, it's super hard to do some what we call negative graph. What is positive? What is negative graph? Besides when, I don't know, you are exploring a graph of the world, between the connection between all the cities. You have a single graph. What do you call like a negative graph? So because of that, it's super hard to extend CPC methods. And it turns out that even when you extend CPC methods, they do not perform well. They quickly go out of memory because you need so many negative examples that it cannot be handled anymore. The good news with BYOL is we don't need negative example anymore. So you can just take your classic pipeline. You have your initial graph. You apply transformations, just simple one, no feature masking, edge masking. Here, what is nice is we are not trying to create negative example. We're just adding information. So it's fine to do this transformation. It's always the same graph. And because we say it's the same, even if we're using transformation, it's not in the goal to do a different negative. So we can do it here. So once you apply this transformation, you process with your graph network, your favorite graph network, you add your predictor, and you do a constant similarity exactly as we used to do. And without any surprise, you do that, and it works. Well, it works. It works in the sense that it is one of the easiest methods, and you have excellent results. In practice, it turns out that if you have a random initialization for your network, it's a very strong baseline. So if you have to deal with network, I would recommend just to take a random projection. But still, it is one of the very few methods that manage to outperform a random projection. Other topic where it has been applied with recommendation systems, where you try to predict, to say it's the same users because they like the same models. The paper got rejected because I think there was some experimental flaws, but the ideas remain the same. There is another paper from Mila where I use this kind of BYOL representations as an auxiliary loss for reinforcement learning, and it works out of the box. So every time it has been applied, the feedback is the following: it's simple, it works. So let's do it. So now I have time for the RL. So up to you.
Perfect. Nice message. So I'm sure there is a lot of motivation now to try a lot of things. Some of the people I know listening this talk are already actually trying it for different things. So, well, hopefully we'll have some feedback to give you in the near future. But in the meantime, yeah, let's go for some questions. If anybody in the audience wants to ask something to Florian, Inigo has the hand raised. So if you want, go ahead.
It's okay. So, like, thank you for the talk. Like, I'm a kind of fan of your method. Well, yeah, from your method that all the DeepMind guys that have worked on it. So, like, first of all, like, the main thing, the thing that I like a lot of this method is because you don't need negative samples. I mean, like, all of us should teach our children and kids with positive samples, so the same for deep learning and networks. So, no, like, in fact, like, negative samples are, like, bad because you don't know anything from your samples in a self-supervised way. So my main question about the method is that what I grasp is that the predictor, like, that predictor is really important. Like, you suggest, for instance, you can change the exponential moving average model with the same network, but you should, like, tune your predictor with higher learning rate, for instance. But my question is that what do you think about, like, the Dino work that removes this predictor branch with some operations like the centering and sharpening, and your views on this? If there can be some other ways that different from the predictor to make the BYOL or BYOL method works. So it's about that, yeah. So the predictor, like, what can be changed instead of, like, or introduced instead of the predictor, and yeah, more or less, it's an abstract question.
No. I really see what your point here. So the question is, well, this predictor is important, okay, and how somehow Dino, which is a very recent work, is like BYOL or different BYOL in the sense it doesn't have an explicit predictor. So first, before answering the question, I would like to highlight the fact that Mathilde Caron has been working on self-supervised learning without negative examples for quite a long time. And she was actually one of the very rare to believe in it and try methods on top of it. And to some extent, she's definitely one of the precursors of BYOL. However, she didn't look for bootstrapping methods. She looked for clustering methods, which can also be seen as pseudo-labels. And in Dino, what she tried to do, with success, it turns out, it seems to be, sorry, is that she have a BYOL-like architecture where she managed to include this cluster. So for people that are not familiar to this Dino work, imagine that you have BYOL, more or less, but instead of having this MLP, what you're going to have is kind of a clustering method, or I didn't have the time to read everything in the paper, so really stop me if I say something wrong, Inigo. But it replaces MLP by a clustering method, just a centering. And then she's regressing the different centering, different centers. Is it correct, Nico?
Like what? Like, can you repeat? Like what they do? Like, what I think they do is just, like, they do some centering and sharpening that they just, like, the centering is just like a moving average of the previous representations, and they do some softmax, some other minor tricks, but that's the main.
So what is important is the following. In the end, what I understand she's trying to do is trying to force a clustering in the process. However, she still uses a bootstrapping methods, and she still has this asymmetry. So she replaces this asymmetry that is learned by an asymmetry that is coded and enforced clustering. So because of that, she still has all the property of this asymmetry and this bootstrapping with the target network. So she's doing a BYOL method, but she's putting more prior in the predictor, and this additional prior seems to help a lot. Something that is, it's not from me, it's from Carl Dodge, that is a co-author of the BYOL, made a very good analysis of this. When you look at the paper, she has very strong results on the classification task. And even if you look at the first page, we show that the network learns to look at really good specific objects. And this may be a bias of this clustering algorithm. It's because the clustering algorithm, to some extent, is always trying to labeling one object because he has one cluster. Then it's going to be super good at classification task. What is missing in the paper is transfer on segmentation or something that is not classification. That is why it seems very promising, but we are missing just a few additional results to say, okay, replace BYOL by Dino. Having said that, when you do need good classification with few labels, go with Dino. The paper is rigorous, plenty of good things. And the second point that is also interesting, I mentioned it quickly, is at some point, just for fun, Corentin, also one of the co-authors, replace this MLP by memory network. And what was funny is if you replace this MLP by memory network, you don't have a direct gradient that flows into the memory, into the value keys. But you still have state-of-the-art results. It means that somehow this memory network was learning implicit negative example. So it was doing, maybe, we don't know for sure, but some kind of negative example, and even itself a form of clustering, a source clustering. Take my word with a grain of salt, we didn't explore it further. Some other works that were super interesting too is Pierre first observed it in some experiments, and then it was really confirmed with one paper by Facebook. It's this prediction is also catching from time to time new eigenvalues from the representation. And it's because this keep evolving, it's super subtle to catch, even at late training, new eigenvalues. And you really see that when you catch new eigenvalues, you can compute it with linear projections. Your performance have a positive drop. So as those positive eigenvalues be captured by new negative examples that are retrained, all those things, it's really too early to say. I'm from reinforcement learning, I'm from empirist perspective, so I'm trying to explain with hands. Some of my colleagues may have another different explanation because they have more information background. Does it answer your question? Because I move in different directions.
No, yeah. And like apart from answering, like you commented in like a lot of other works and interesting things. So like, thank you.
Okay, so maybe we can go to one more question. Juan Raul, please go ahead if you want to ask.
Okay, thanks for the presentation. It was quite insightful. You know that you mentioned like these different modalities, right? Mm-hmm. Like audio and so on. But your original work is in vision, right? But I was wondering about like the 3D part. Like when you have this data augmentation that you mentioned, mm-hmm. What about like, for example, more like occlusions or like you have literally a different view from the camera. So I don't know. I was wondering when if you think that it would be possible to use this method for like a 3D vision.
I was looking for. Question: yes or no? Yes, in the sense that it's transformation, which is a valid one. So actually, I reviewed a few papers on top of it. So it seems like a valid thing. Yet, you're going to miss something important. It works because it's unlabeled data. So if you have a simulated world, when you can have as many 3D views as possible, it's worth it. If you're working in robotics and you have a 3D world and you want to look at representation, it's worth it. Sometimes you can apply a scene to record. Yes. If you're dealing with real images with 3D views, I don't think it's a good idea because you're going to be limited in the number of times you can apply such transformation.
Thanks. And I think that it would be a really interesting experiment. Like with this method, like I try to see, for example, with the classification or these downstream tasks, how can deal with the, let's say, like this example, like you have an occlusion or you have like the dog with a very different view. That would be interesting to see if the method can deal with this.
But do not forget that what is key here is the number of data on the training time. So even in BYOL, we only use ImageNet. So you can say, okay, your data is not very important. The number of data is not very important. We train it for 1,000 epochs. It means that for every image, we have 1,000 transformations. So it's very important that you either need a lot of data or a lot of time when you're going to apply your transformations. And with 3D in real images, I don't know if you have access to this amount of data. But I can be wrong.
I see. Yeah, okay. Thanks for the presentation again.
So Florian, maybe we have time for one more question.
Yeah, then I would like just to show something on the array because I think it's quite important. You're going to see, but we have time for next question. Yeah.
Okay. Okay. So let's go, Leon, for your question.
Okay. Hello. First of all, thank you very much for the presentation. It was very, very interesting, and your work is outstanding, in my opinion. So, yeah. The last question just made me realize that this approach could be also used in other places where contrastive learning has been already used. And I was thinking, well, I'm working in local feature extraction with deep learning approaches, and a couple years ago, I'm working in variants of Superpoint, which is you already know it.
No, but I'm understanding what you're saying.
Yeah, well, it's an approach that uses an image and then applies random homographies to this image, and then tries to extract local features, and then uses this approach of trying to locate the same features in one image with an homography, and then another one with a different homography. And I was thinking if maybe this approach could be used like fused with these BYOL and bootstrapping approaches you're explaining. What do you think
have
about
input?
it?
Can you transform this input?
Sorry?
You have an input?
Yes.
Can you transform it? I don't know.
Of course. Yes.
So then you have your answer.
Okay. Yeah, I was only thinking if you thought anything about that.
Surprisingly, BYOL is not too tricky to tune.
Mm-hmm.
Still, so it's machine learning. So when you have very specific task, with a lot of past human expertise, machine learning is still not always as good as other methods. So especially when you're dealing with geometry and things like that. So it was try. Yeah, there is no guarantee that it's going to work, but it's worth a try.
Okay.
Thank you.
Very much.
So Florian, you wanted to show us something, or Pablo wants to ask also something? I don't know, whatever order you prefer.
Pablo, go ahead.
Yeah, no, it's just a small question because as I told you the other day, I'm trying to train with BYOL. Which thing you think it's going to obtain better performance? Train the BYOL with ImageNet and then using the representation of images in a classification of different domain, or trying to train the BYOL with the domain you are then going to classify? Because, for example, I'm working now on intestines and the bowels. So it's a really, really different domain from ImageNet. Okay. So I was wondering, which one do you think is better approach?
So I think this table may answer your questions. Is here it was pre-trained on the ImageNet.
Yeah.
With BYOL, and you also with a lot of different data set. Here it's food, so it's a bit like image. But you have things like, what is it? DTD, which is a texture data set. It's not here, but I also trade on an open source medical data set for cancer cells. And what you observe is when you start from scratch with the initialization, with the data set, you have a bit of lower score than when you start from a pre-trained checkpoint. Even when it's completely out of distributions.
Okay.
In my case, when I was dealing with cells, so it was pre-trained on dogs and cats, it's ImageNet, and cells were pink pictures with, I don't know, it's of cells, it's biometric pink pictures, completely out of distributions. And it was better than learning from scratch. Having said that, what is important is to use a pre-trained network. It's not clear if it's better to use a pre-trained network on with a supervised learning method, or is it better to train pre-trained network with self-supervised learning? So from time to time, the self-supervised learning approach is better. From time to time, the classic pre-train is better. So there is not a gap that is big enough, so I would recommend no one or the others.
Yeah, it's train both.
Yeah, but start from the out. It's not but to your question, is it okay to pre-train with an out of distribution data set? My answer is yes.
Okay. Okay, thank you. Nice presentation, by the way. Very interesting.
Okay, so yeah, thanks a lot on behalf of all the attendants and also myself for the talk. And yeah, you wanted to tell us one more thing, so please go ahead.
Because there's a lot of there's plenty of students here. There is something that I would like to emphasize. Is it seems like a very simple idea. As you take an image, you regress it, and what is new in BYOL in the end, it's okay, you just remove that. That's all. And when you see a presentation like that, what you're going to think is, okay, I'm going to take an architecture and an algorithm, I'm going to try to tweak it. And sometimes it's going to work, and it's going to be easier, and it's good. And it's not the way it works in research. Because a lot of people think, okay, how did you come up with just adding just this one? And because it's really trivial, that's all. And if you look at the people working in self-supervised learning, you have Jan Lucken, you have Hinton that work on it, you have Cumming Hayes that invented the ResNet. So those people are smart. Why they didn't think about it? And that's why I tend to emphasize that we have this idea not because we were working in vision, but because we start from another algorithm that was from reinforcement learning. So I'm not going to go into the details, but what happened is at the beginning we had a kind of a complex reinforcement learning algorithms. Without having all the details, we had a kind of complex reinforcement learning algorithm that was trying to learn representations with pixels. And we know that it works, and what was surprising that these algorithms work better than CPC in array fashion. And then what we have in this algorithm is kind of a G function here. We have a RNN, and we use G functions. It was in order to learn a representation of the image. If you want more details, you have the paper here. And it turns out that, okay, we say it's very surprising that an algorithm in reinforcement learning was better than other algorithms such as CPC. So we at some point we created a team to say, okay, let's try to apply in vision. And it turns out that when we turn it into vision, we had this first graph. This first graph, I'm not going to go into the details, it comes to something like that. Because we come from reinforcement learning, we don't like to have two ResNet, and we turns out to have an EMA. And but what is important is this predictor. What is the key here? We didn't decide to put it back. It's just an artifact from the previous algorithms. So we have an array algorithm that worked, and this G was completely meaningful. On this one, we switched to vision that we just forgot to put it, because I forgot, not exactly. It was natural to keep it this way. And this was BYOL. It's not like we started from simply and we say, let's try to tweak around. It's the fact that we started from a completely other algorithm into another topic, which was when you think about it this way, it's very intuitive to build it this way. And then when we come back to vision, we have this predictor. So it is this story that I want to highlight is when you do research, don't try to tweak around. Move from one topic to another. Try to think about why you're doing it. And it turns out that the correct solution is going to emerge by itself.
Thanks a lot. That's a very nice message to wrap up the talk. So again, thanks a lot for the very thorough explanation of this approach, and also for all the tips and hints that you have been given, all the questions. I think definitely you may be in a thank you note from following papers from this group.
Folks, if you have any questions, feel free to ping me at any time.
So well, anyway, I think we probably need to wrap up here the seminar. So again, thanks a lot for making the time for this. And well, it's always weird to wrap up the seminars now. It's just like bye and we can go instead of going to have a beer to the cafeteria. But well, we'll keep that for whenever we can. We definitely owe you a round of tapas here.
Okay, only if the second one is for me.
Okay, so yeah, see you soon, hopefully.
Bye-bye.
Thanks again. Bye-bye.
Bye. Have a nice day.
Bye.
Thank you. Bye.
Bye. Thank you very much.
Bye.
Bye.